second talk today afternoon. It will be by Dennis Steff, again from the Arctic University of Norway. And Dennis will talk about uniqueness of submaximally symmetric parabolic geometries. Please, Dennis.
Okay, so thanks very much, Yosef. And thanks very much to the organizers, Katya, Omid, Pavel, for organizing this fantastic workshop. I really enjoyed it. So I'm going to first of all start off with some apologies that sorry that we couldn't make it to Poland this year, and hope to see you all in Norway next year. So this is where we are right now. This is in Someroya. The weather is actually pretty bad today, and but we had some pretty nice weather yesterday, and this is where we are here. So I'd be happy to show you guys around, hopefully next year. Okay, so I want to talk to you about a topic that's near and dear to my heart. My first project in parabolic geometries related to symmetry gaps. Okay, so I'm going to give you some examples of such symmetry gaps. So let M and S be the maximal and submaximal symmetry dimensions. And here's a list of some examples. Some of them very classical. So this second order ODE, two-dimensional projective, 235. This goes back over 100 years, right? This goes back to work of Tresse at the end of the 19th century. Cartan here for 235, 1910. Okay, so in each case, I've given the maximum symmetry dimension, and you can see that there's a substantial gap occurring. Okay, so in each case, I've also listed the G and P pairs. There's some geometric structure, some parabolic geometry associated to this, and you have some model space. So G, P, G mod P. Okay. Right. So here I've listed some of these in low dimensions, but also some in higher dimensions. Okay, and there's quite a big gap occurring here. Okay. So in 2014, so this first paper I wrote with Boris. So we gave a framework for studying such symmetry gaps, and we found many values for this instances of such submaximal symmetry dimensions for parabolic geometries. Okay, so it didn't resolve it for the problem for all parabolic geometries. So for the complex case and the split real case, it was quite a complete result. But for general real forms, there's still a lot of research that can be done. So Boris worked on the CR case, worked on the Riemannian and Lorentzian conformal case with Boris Dubrov, Boris and Lenka Zalabova and Henrik Winter, almost quaternionic cases. So there's still, for general real forms, there's still work to be done. But what about parametrizing structures? So locally, there exists a unique maximally symmetric model, okay, locally. So this is the so-called flat model. Okay, so my talk today is about addressing the local classification problem for submaximally symmetric structures. Okay, and I'll give you some examples, also show that, I mean, to make this a reasonable problem, we're gonna have to narrow down some hypotheses, okay, but we get a nice answer in the end. Okay, I should also mention that there are, of course, techniques for classification of geometric structures, and in particular, this problem will be a problem about homogeneous structures, and so we'll say a bit more about that in the discussion period. In January and February of this year, I gave this Greek lecture series about classifying homogeneous structures, and I emphasized one particular method called Cartan reduction that you've seen. I illustrated it in low dimensions, and it's a general method, so in principle it will apply. But the fact is, it's very, very cumbersome to apply beyond low dimensions. Okay, so part of this story is how do you efficiently classify geometric structures, homogeneous. Okay, so outline of the talk. I'll start off with some examples, enough to state and formulate the main theorem. Then I'll do a recap of this framework for symmetry gaps here. I won't go through a lot of detail, just kind of summarizing what some of those results are, so you get a general picture of what the story was. And then we'll spend some more time giving some details for the main theorem. I want to concentrate on one particular example. We'll go through that slowly. So you could see what the main idea is there, and then I'll sketch out for the most general case how things go. But that's quite similar, but just a little bit more technical. So we'll see that later. Okay, examples and made there. Okay, let's start off with rank 2 examples here. Okay, so start out with second order ODE. So y double prime is equal to f of x, y, y prime. This defines geometric structure. In Pavel's talk, this also can be referred to as a para-CR structure or a curved skate geometry, something like that. But just to put it plainly, so if I talk about symmetries here, what's one way of defining that? Here I'm talking about symmetries under point transformations. So these are vector fields in XY space that you could induce their action up to the second jet. Okay. And I want these prolonged vector fields to be tangent to that equation submanifold in the second jet. Okay, that's one way of formulating things. The maximum is 8. Submaximal is 3. This 8 is very special. It's SL3, as was mentioned in Pavel's talk. What about this submaximal symmetry dimension, 3? So here's the list of models. They're all homogeneous, locally homogeneous. Okay, it's quite a complicated set, right? I mean, there's some parameters appearing here and here, isolated models over here. Whenever you have a parabolic geometry, there are fundamental invariants. And for this particular geometry, the fundamental invariants take the form of 2 relative invariants, so often called I1 and I2. I2 is very easy to state. It's taking this right-hand side, differentiating 4 times with respect to y prime. This one is much more complicated, but don't need that expression here. So most of these, both of these I1 and I2 are non-zero everywhere. This last one, I2 is equal to 0. This is in particular that tells us that this describes the G of these equations for some projective connection. There's another nice model that I just want to mention here just to illustrate why we need to kind of put some more reasonable quick conditions on the problem. Okay, so let's look at y double prime is equal to x, y prime minus y, all cubed. This is I2 is equal to 0. I1 is non-zero, but not everywhere. Okay, it's actually vanishing along a hypersurface. Okay, so if you look at its symmetry algebra, which is 3-dimensional, it's just SL2, it has intransitive symmetry. Okay, so locally, this model at a point along this singular hypersurface is not going to be locally equivalent to the same model at a point off of this hypersurface. Okay, and just to note that off of this singular hypersurface, it's going to be equivalent to this model, this projective model that's given right here. Okay, so when I say classify, I want to be working under some reasonable genericity assumptions, as was described in Joel's talk. So let's work off of some singular hypersurface. In particular, I'm going to formulate it as working at a point along which harmonic curvature is non-zero. These are components of the so-called harmonic curvature. Okay, so a nice point. Okay, in a neighborhood of a nice point. Next example, 235, also discussed in Pavel's talk. So rank 2 distributions with generic growth in dimension 5. So here, this was studied by Cartan in 1910, his famous 5 variables paper. The maximum is 14. It's the maximum symmetry is maximally symmetric model is unique. The submaximal symmetry dimension is 7. Here's a model on XYPQZ space. I'm defining the rank 2 distribution like this. Okay, where f is a function of 5 variables. Okay, so actually any 235 can be locally always written in this way. You can choose coordinates to do so. You need a genericity condition to get that growth, and that's the double derivative of f with respect to q is non-zero everywhere. Here's a list of models. One parametric family, one kind of separate model here. There's a fundamental invariant here, the harmonic curvature. It's a so-called binary quartic. That's famous Cartan quartic. And the multiplicity of the root type is 4 everywhere. So this is called root type n. Okay, so parametric family here, complicated set of models here. Here's another model that was discussed in Andreu's talk. So G2, P2 type geometries, also called G2 contact structures, maximum is 14, submaximal is 7. But here, locally, there exists a unique G2 contact structure with submaximal symmetry. Okay, nice situation over there. Let's go through some organization of these Lie algebras, this modeling data. Fix a semi-simple Lie algebra, pick a parabolic subalgebra. This defines a grading associated to it. There's a grading, there always exists a grading element such that the eigenvalues for the add Z action, so these GJ levels, are precisely those eigenspaces. Okay. Just a warning, however, this grading that I've introduced is just for convenience. Okay, what's more important is this filtration. The filtration is P invariant. The grading is not P invariant. It's only G0 invariant. Okay. Filtration. The distinction between filtration and grading is extremely, extremely important. Okay, so here are some root diagrams and Dinkin diagrams. For SL3, you have this stratification into levels running from -2 to 2. So what's this filtration? It starts out with the -2 part being the whole thing. Then you have everything from 2 to -1 being the G-1 filtration, then smaller, smaller, smaller. So it's a decreasing filtration. As you increase the integer, then you get smaller subspaces. Similarly for the G2 geometries here. Okay, so here's G2, here's its parabolic subgroup. And then you have the quotient being represented by what's in black here. This G-1 level, that distinguishes a G-invariant distribution on the homogeneous space G mod P. And yeah, so the filtration on that quotient here gives me a distribution, then the derived gives me this rank 3, then fills out to rank 5. In the G2 contact case, we have a contact 5 manifold, rank for contact distribution, and then what I have here, the geometric structure is a twisted cubic on that projectivization. Okay. Note that here, this 0 level is GL2. Over here, this 0 level is also GL2. This rank, this G-1 level, you can see it's a Sim3 representation for this GL2. Okay, and then you have this transverse Reeb type direction sticking out of that contact, transverse to that contact distribution. Okay, and curved versions, second order ODEs in the first case, 2, 3, 5, and G2 contact. Let's go up to rank 3. Consider 5-dimensional Legendrian contact. Okay, so this is a generalization of second order ODEs, referring to Pavel's talk. So he called them Paracr structures. So in this dimension, okay, so we're considering a 5-manifold and a rank 4 contact distribution that's split. Okay, unlike in the second order ODE case where it's a rank 3, dimension 3 manifold and a rank 2 contact distribution split into lines for that geometric structure. Here, this splitting is into rank 2 subbundles, both of which are isotropic for a natural symplectic form on C. Okay, now these could be, a priori, these could be integrable in the Frobenius sense or not. Okay, so 2 basic invariants are 2 torsions that obstruct the Frobenius integrability of either one of them. Okay, but then further beyond that, there's something called binary quartic invariant. And I've written it as W. It's an analog of the Weil curvature from conformal geometry. So submaximal symmetry dimension is 8, maximum is 15. How many actual models? Oh, okay, actually before that, just to make things more concrete, in the case that one of these torsions vanishes, so this say tau F, you can locally describe this as a complete system of second order PDEs. So one dependent variable, many independent variables. You could always write it like this. It may not be compatible or not. The compatibility condition is encoded by the vanishing of the other torsion here. What about models? there exist exactly 3 inequivalent models with 8-dimensional symmetry each with exactly one of these invariants being non-zero. Okay, so this is coming out of this recent work. When these torsions both vanish, just to make things concrete, then this is going to be a compatible system of PDEs, and this is what it looks like. So this came up in classification program with Dubrov and Medvedev recently. A different sort of real form of this geometry. So real CR hypersurfaces in C3 with Levy form that is either positive definite or indefinite. Here's a model. Group G is SU13. So this and this, they complexify to the same thing, SL4C. This is a split real form. If you take SL4R, that's a split real form. This is not a split real form. Here, the situation is quite complicated for submaximally symmetric models. This goes back to Loboda. Okay, there's several parametric families here for these 7-dimensional models. In the indefinite case, the situation is better. There's a uniqueness result. Okay, so locally, there's just one, this Winkelmann hypersurface, and this is what it looks like. So this slide is to just lay down some definitions so I could formulate the main theorem. So our starting point, I mean, so all of that was describing concrete structures downstairs, local coordinates, how you might like to think about them. But how I like to think about them is really upstairs. So for me, the starting point is to use this, what I call the fundamental theorem of parabolic geometries, that there exists an equivalence of categories between regular normal parabolic geometries and underlying geometric structures. Okay, so well-known, beautiful result due to Tanaka, Morimoto, Chap, and Schickel. Okay, so the upshot is I want to study symmetry upstairs, where things become much more uniform. Okay, so let's run through the definitions. Let's take a parabolic geometry of type GP. So this is a principal P bundle, right principal bundle, with a Cartan connection. So this is a co-framing, one form on this total space, this Cartan bundle with values in the Lie algebra. It's equivariant, reproduces the vertical, fundamental vertical vector fields. You get a notion of curvature, and you could evaluate this on the co-framing and get the curvature function, which is horizontal. So it annihilates vertical directions. And so you can regard this as a function on this total space with values in this space, okay, where I have this G mod P star appearing here, via the killing form, okay, for semi-simples, that's non-degenerate. I get a P equivariant isomorphism to this space. Okay, so this G plus positive part of G. This guy's flat, the geometry is flat if this curvature is 0. Okay, so these conditions, regular, normal, what are those? Regular means that, well, one way of formulating it is that the image of this kappa is, so it's valued over here, is valued in the positive subspace with respect to Z, this grading element. Normal, this is looking like a homology space, a space of 2 chains, and there's a homology differential that squares to 0. And so I could look at its kernel, and so that's the normalization condition that we're going to use. Okay, regular and normal, kappa being in the kernel of this del star. Being in the kernel of del star, I could quotient by the image and define harmonic curvature. This is valued in a homology space, but rather because of regularity, it's valued in the positive part of this homology space. And what's nice, because that's well known, is that this space is completely reducible. Okay, so you have this action of the fiber group P everywhere here. In particular, this space, it's completely reducible. So the positive part of P acts trivially. So to understand this, we only need to understand the G0 action. Well-known results is that, so if you want to characterize flatness, so locally being isomorphic to this flat model being G mod P. So kappa is equal to 0 is the definition, but it's sufficient and yeah, it's equivalent that actually only harmonic curvature is 0. Okay, and in fact, as I mentioned, the maximally symmetric model is being maximally symmetric is unique. So I could reformulate being submaximally symmetric. So what is the submaximal symmetry dimension? It's the maximum dimension of the symmetry algebra of this upstairs structure such that harmonic curvature is not identically 0. I'm going to introduce a tighter definition here. So adapted to, well, I know that harmonic curvature takes values over here, but sometimes, so it may split apart as a direct sum of irreducible submodules for P, but actually only G0 is relevant. Okay, and that's reductive. So I can actually get a direct sum decomposition. Okay, so suppose I choose one of those irreducible pieces there. Okay, so this is V. So I'm going to say that a geometry is of type GPV if it's of type GP and harmonic curvature is concentrated in that particular submodule. And analogously, we're going to define the submaximal symmetry dimension relative to that submodule. Okay, so just everything concentrated, harmonic curvature concentrated in V. Okay, so that's enough to be able to formulate the main theorem that I'm introducing today. So we're going to put some nice conditions. So let G be a complex or split real simple V group. Okay, so I gave you an example of what's split real versus something not split real. But the moral reason why this is nice to restrict to is that we're going to be using representation theory, and we're going to have extremal orbits. We're going to have all that nice stuff from representation theory, weights and roots and everything. So that's a really nice setting to be working in. Let's let P be a parabolic subgroup. Let's take a regular normal parabolic geometry of type GPV, okay, working upstairs, where we're selecting a particular submodule to focus on. Now let's look at something submaximally symmetric, okay, something with symmetry dimension, this SV. So here's the main hypothesis. Suppose that, I mean, you saw in low dimensions, things are not very nice, but as soon as you hit the next one, so rank at least 3, or actually there's one nice case in the rank 2 setting, then about any nice point, so where harmonic curvature is non-zero, then conclusion, the geometry is locally homogeneous, and in the complex case, it's locally unique. In the split real case, locally, it's one of at most 2 possibilities. Okay, and this result is constructive in the Cartan sense. I could give you those models. Okay, I have to tell you what do I mean by this Cartan sense. Okay, so that's the result, a nice, basically unique uniqueness result for submaximally symmetric structures. Okay, modulo these hypotheses. Okay, so let me review some of this framework for studying symmetry gaps. So given GP, we have this grading, I said, and constant gives you an isomorphism between these homology groups and these Lie algebra cohomology groups. And we want to just understand the G0 module structure. This is easily computed using Constant's theorem. Okay, I'm not going to drag you through all of this representation theory, but just it's easily computable. Okay, so you have some parameterizing sets, and then you have some modules, and then by the theorem of highest weight or lowest weight, these are completely determined by their lowest weight. So I just need to describe these lowest weights. And that's what constant does for you. But also we have explicit lowest weight vectors. Okay, this dot is the affine action of the Weil group. Okay, so there's nice Dinkin diagram recipes that allow you to do this. Okay, so basically it becomes one-liners to rediscover this fundamental fact that, for instance, for 235, your fundamental invariant is a Cartan quartic. Okay, but I'm not going to run through all this, but just remember these are easily computed, okay, from representation theory. The second ingredient is Tanaka prolongation. So what I call extrinsic Tanaka prolongation. So let phi live in some G0 representation. Going to be thinking of this as the value of harmonic curvature. Then let the non-positive part be G minus and the annihilator of phi. And then we're going to propagate this to the positive part. So those that are at level AK, these are elements of GK that bracket with everything in G minus 1 to be in the previous level. Okay, so this defines a graded Lie subalgebra. Of particular interest are non-zero values for phi living in this harmonic curvature space. Maybe I'm going to restrict to some submodule. maybe I'm going to restrict to some orbit. Okay. One can ask, do I actually get into positive prolongation? Okay, so there are some instances, many instances, where as soon as you, sorry, I should put non-zero here. As soon as you turn things on, then you never get into positive prolongation. Okay, those we call with Boris prolongation rigid, PR. Okay, so just as an example, one of the results we had was that if P is maximally parabolic, so that means you have a single cross on the Dinkin diagram. So for example, for 2, 3, 5 or G2 contact, this GP is PR. You don't get into positive prolongation. Okay, so let me briefly now summarize some of the main results that that's important for today. So from our paper, of course. So fix any GP, then the submaximal symmetry dimension is bounded by some universal upper bound. Okay, universal in the sense it applies for all cases here. Doesn't matter if it's split real or not. Okay, so here you have geometry talking about symmetries. Here you have algebra. Okay, so this is the maximum dimension of this Tanaka prolongation, subject to this condition of phi being non-zero. Okay, analogously have these results in these more restricted settings. In the complex or split real simple setting, you have efficient Dinkin diagram recipes to compute this upper bound. So for instance, there's a recipe starting with this, you could compute the number 7. Okay, but these recipes are just as easily applied to the E8 setting. What about asserting a priori that you have equality? So it turns out S is equal to U almost always. You're going to get some exceptions only when the rank is 2. Okay, this is under this complex or split real hypothesis. For the non-exceptional cases where you have equality, then you get any submaximally symmetric structure is locally homogeneous near a nice point. Okay, so I know I'm going to be, when I want to parameterize these structures, I'm working with homogeneous geometries. Just as a small side remark, but an important one, in fact, we proved a much stronger result with Boris. Okay, so it's not just in the homogeneous setting, because we didn't want to assume a priori that submaximally symmetric structures are homogeneous. Okay, so here, if you take the symmetry algebra and then you pick a point, any point, apply the Cartan connection to it, you get a filtered Lie algebra, and you take its associated graded, okay, you get a graded Lie subalgebra of G. And regardless of whether it's homogeneous or not, you get this inclusion into this extrinsic Tanaka prolongation at any point. Okay, so we did this on an open dense set using a Frobenius type argument in this first paper. But when we studied jet determination, so we needed to be able to assert, well, some nice things about symmetries. We needed this result everywhere, and in fact, we were able to push that through. Okay. Okay, so before I get to some of the specific details, let me just emphasize some points, and I'll come back to this also in the discussion. How do we exhibit a homogeneous model? Many of you like exhibiting it in terms of coordinate models. Okay, so here for 2, 3, 5, these are submaximally symmetric models. Okay, and it's nice and concrete. I could shove it into Maple, find its symmetries, get it in terms of some generators, vector fields. You can think about it more abstractly in terms of a Lie theoretic model. So just take the Lie algebra generated by this, and then F0 would be the isotropy at a chosen generic point. Okay, these are homogeneous models. This is an infinitesimally effective pair in that the isotropy representation of F0 on the quotient, F mod F0, is faithful. Okay. We have an F0 invariant filtration. In general, you're going to have higher parts, but remember, 2, 3, 5 is prolongation rigid, so things stop right here. But actually, there's another way of describing this. Cartan, I like calling it Cartan theoretically, okay? As opposed to Cartan geometrically, I'm going to phrase it purely in terms of algebra for this homogeneous setting. Okay, so what do I mean by that? So any homogeneous parabolic geometry that is infinitesimally effective admits a description as, well, an algebraic model as the following. An algebraic model is a Lie algebra such that, number 1, F is a filtered subspace with filtrans. Okay, remember G with P being selected, it becomes filtered. So since F is a subspace, I'm just going to restrict that filtration to F. Okay, so I get filtrans. And of course, when I have filtrans, I can take its associated graded. This is going to be a graded subalgebra of G. G is also graded. Since I'm homogeneous, I'm going to then here, the negative part is full. Okay, it's all of G minus. In particular, this tells us that F mod F0 is isomorphic to G mod P. Second hypothesis, F0 inserts trivially into curvature. What is curvature? Curvature is the deformation, the difference between the ambient bracket on G and this F bracket. Okay, so you could view this function that I've defined here as living in this space, but because this is equal to that, then this is equal to this space. Okay? And when you land in this space, when you live in this space, then you have a notion of what being regular and normal means. Okay, so it's in the kernel of this del star, and it's in the positive part. Okay, this is not a new definition. This is just in the literature, it's been referred to as, for example, algebraic Cartan connection, but that's regular and normal and is injective. But that's kind of a mouthful, so I prefer to just call it an algebraic model or Cartan theoretic model, just to emphasize the distinction between this and what I stated on the previous slide, this Lie theoretic perspective. Okay, so this really comes about by taking the Cartan geometric perspective. It's homogeneous, fixing a point, and this is the algebraic data that results from that choice. Okay. Given a G and P, let M be the set of all algebraic models. First of all, M is partially ordered. F may not be the full symmetry algebra for your model, okay, but it's partially ordered in the sense that, well, you say F is less than or equal to F prime if there's a Lie algebra injection from one into the other. And secondly, M admits a P action. And really so you could use these definitions and verify that, or you could think about what I just said about how this arises, namely from the choice of a base point. Choose a base point, but if I move up and down the fibers, then everything just changes by an adjoint action. Okay, so I have an action on this set. Okay, so classification strategy for homogeneous models, phrased in this language, I want to classify the maximal elements. So with respect to this partial ordering, with respect to that P action, but those maximal elements that have harmonic curvature non-zero. Okay, so that's for all homogeneous structures. But yeah, we were going to restrict this to talking about the submaximal ones. Okay. Now, those are some definitions. There are some immediate consequences that help you along the way. Namely, if you have an algebraic model, then this is a filtered Lie algebra. S is a graded Lie subalgebra. We saw that in the definition, F0 inserts trivially, but actually it also acts trivially on kappa. It annihilates kappa. And then further, if you take the associated graded, this graded subalgebra is contained in this extrinsic Tanaka prolongation. Okay, so this of course follows from our result that we had with Boris, but being in the homogeneous setting, excuse me, you could get really a much simpler proof here in this special setting. Okay, so for lack of time, let me just skip these details. It's not very difficult, but those are some of the main points, but those facts really help you in looking at classification in this manner. Okay, so what's this canonical curve model? Okay, so fix a G, P, and a submodule. And let's suppose that that submodule has a lowest weight vector. Okay, so this is stuff that comes out of this constant black box that I mentioned earlier. Let's take F to be this extrinsic Tanaka prolongation with input phi 0. This is a filtered subspace, right? It's a subspace, so I restrict the filtration from G to it. But now I'm going to deform the bracket by the cochain. Okay, what do I mean by that? Well, these are elements in cohomology, but via constant theory, there's this harmonic theory that allows you to identify such lowest weight vectors in this quotient with two cochains that are harmonic. Okay, there's a natural Laplacian, algebraic Laplacian. Of course, I mean, this is just a definition. I mean, a construction, is it actually well defined? I mean, this is some subspace of G. Phi 0, it has some output once I shove two vectors into it. Is that output even in this subspace? And it turns out, yes, it is almost always. Okay, there are exceptions again when the rank is 2. Is the Jacobi identity satisfied? Yes, it is. Okay, so so this gives a construction of an algebraic model, and so this one is what I'll call here the canonical curve model of type GPV. Okay, the dimension of F here realizes the this algebraic upper bound, and so this gives us a construction of a submaximally symmetric model. Okay, this relies on the following facts. So in terms of identifying what this is, so how do you compute it in practice? So remember, the inputs for these can be any non-zero vector in either a V or all of H2 plus. Turns out this is maximized on lowest weight vectors. So you only need to test lowest weight vectors, okay? Or rather, anything in the orbit generated by these things. Okay, so now our classification problem for the task that I set out at the beginning is classify up to this P action all algebraic models whose associated graded is this Tanaka prolongation for some lowest weight vector. Okay, so let me give you about 10 minutes or so, I think. So I'll give you some ideas here, focusing on the simplest case, okay, the G2, P2 case. Okay, so here's the G2 root diagram that was discussed earlier and in Andrea's talk. So I have simple roots, alpha 1 and alpha 2 being long. Let me define the corresponding dual basis. So this spans the Cartan subalgebra. This is Z1, Z2. The grading element, because I'm working in the P2 case, is going to be Z2. Okay, so this stratifies things into these levels. G0 is GL2. You have an SL2 triple there, and then you have the grading element. Black box, constant, gives you this output with this lowest weight, and this lowest weight vector realized as a 2 chain here, but via the killing form, I could convert this to a 2 cochain. So this would eat something from the minus alpha 2 direction, and this from the minus alpha 1 minus alpha 2 direction, and spit something out here. What's the extrinsic Tanaka prolongation adapted to this? It's G minus plus annihilator. You don't get into positive prolongation because this is prolongation rigid. This is a maximal parabolic. Okay, and this is what it looks like. Okay, so our goal here is to classify algebraic models with associated graded, being this A. Okay, now I have this freedom to work with this P action to kind of normalize the embedding into G, and I will do so. Okay, so I'll break this down to 2 steps. Step 1, determine this subspace. Okay, so and here the distinction between grading and filtration is absolutely essential. So you should think about what's given as A as being like the leading order parts of this embedding. Okay, what we need to determine are these higher tails. Okay, so let's start with the 0 part because there's a lot of restrictions on the 0 part. Okay, it acts algebraically. Things are nice. Okay, so let's take some element T in the 0th filtrand, whose associated graded has leading is precisely this. Okay, so this T is equal to this guy plus some higher order tails. So in the 1 piece and the 2 piece, etc. But then just use the adjoint action by P plus. So notice that for all these roots in the positive part, the pairing between Z1 plus Z2, Z2 and all of these roots is non-zero. Okay, so then I could just use the P plus action to normalize those tails away. So that, so they're gone, and I just have this nice semi-simple element inside the Cartan subalgebra. So in my 0th part of this F. Okay, so I have this A. So what about the other tails for the other directions? Here's my A. let me define a complementary vector subspace in G, but I'm going to do it in a nice way, so adapted to the root space decomposition, because this is add T invariant. So I could write this embedding, this F sitting inside G, as a graph over A. Okay, so in other words, just concretely, if I have any element in F, I could write it as something in A, those leading order parts, plus these higher tails. So I call this the deformation map, okay? But higher tails. This delta, it lives in what space? Well, it's an A star tensor, the complement, a perp. It's of positive degree, okay? So all these higher tails disappear when you pass to the associated graded. But because this decomposition is add T invariant, this map is heavily constrained. It's annihilated by T. So what this is saying is that delta is living in the subspace of this vector space. That's a sum of weight vectors for weights that are multiples of this starting weight. Okay, so that's heavily constraining. Okay, just from this initial seed. Okay, in particular, notice, I mean, you have coefficients that are of opposite sign. But if you look at this space over here, A star, right? I mean, this is all, A was all negative stuff or non-positive stuff. A star is all non-negative stuff. A perp is all non-negative stuff. Okay, but if I want to be multiples of this thing with opposite sign, you're heavily constrained. Okay, in fact, delta has to be equal to 0. So F is equal to A as filtered subspaces. Okay, so it's just an eigenvalue type argument here. Step 2. Okay, we understand the embedding as a filtered subspace. What about curvature? Let's determine curvature. Again, using the fact that everything is heavily constrained by this weight. First step, the lowest degree part of kappa is harmonic. This is a well-known fact you can find in Chap Slovak. This lowest part, if you look at the degree here, so the Z2 degree is 1. So F0 annihilates kappa, so T annihilates kappa. So again, this is constraining on the weight, possible weights for kappa. We are interested in multiples of this weight mu. Okay, this is something that lives in two chains or two cochains. Okay, so you could write that weight as alpha plus beta plus gamma. Okay, where alpha and beta are distinct. Gamma is either is a root or 0. R should be non-negative, and that's because of this lowest degree part being harmonic. It should also be integral, right? Because the everything's integer valued here. The highest weight is 3 alpha 1 plus 2 alpha 2 for G2. And so this puts a constraint on where gamma can live. Okay, it's some roots or 0. So it's living in this range over here. And so now from this inequality, I'm going to apply Z1. Z1 on minus lambda gives you minus 3. Over here, I get Z1 applied to sigma. Sigma is a multiple of mu, so we get R Z1 of mu. Mu, the Z1 degree is minus 2. So you get this. Okay, and so you get this inequality. R is less than or equal to 3/2, but R is integral. So therefore, R has to be equal to 1. So kappa is necessarily of lowest degree, but the lowest degree part is harmonic. That's irreducible. You have a unique lowest weight vector. So this kappa has to be just a multiple of this lowest weight vector. So you have a parameter. Now you use whatever residual structure group you have. You have this non-zero parameter to just rescale. Okay, so over C, you can always rescale that to 1. Over R, you might have at most a plus or minus 1. Okay, so conclusion, we get only the canonical curve model. So this is what I mentioned earlier. Over R, at most is a plus or minus 1 after the rescaling. But what's striking about this, compared to like classical ways of doing classification, I did not use any full structure equations for G2P2 geometries. That's unnecessary for this problem. Okay, it's a lot more efficient, and you make an efficient use of G2 weights in this calculation. Okay, and it can all be done by hand, whereas if you do classification problems for more general problems, of course, using structural equations is very useful. Okay, maybe a couple minutes just to kind of run through some ideas. General case, more technical, but in using specific knowledge coming from constants and lowest wave vector, we need data about the A0 part, this annihilator. Okay, there's some secondary grading that's introduced. Okay, there's a nice trick to simplify things. It was mentioned by Armand, I think, this work of Andy Chapp, this twister kind of idea. So basically reformulating the problem here in terms of problem kind of downstairs on a twister space. Why would you do that? Well, first of all, example, for second order ODEs, you have some cases where you have projective connections. Okay, so you can for that class, you could regard this as projective geometry that you're studying. Okay, but why would you want to pass down to the twister space? The benefits of this twister space is that you get prolongation rigidity always. Okay, so you never have you always have F1 is equal to 0. Okay, how is that used? Basically, the story is just you have a special weight, and it's if you expand it with respect to the basis of simple roots, you have coefficients of opposite sign. Okay, so it's basically the exact same idea, just a little more complicated, and you got to get used to all this representation theory, but the idea is basically the same. So strategy, pass to the minimal twister space. As I said, F1 is equal to 0. Pick an H0, so something in the Cartan subalgebra, in the annihilator of mu. Okay, so pick one, a generic, this is like a generic guy. First, you use the P plus action to normalize a generic element here. You succeed in doing that. Then you do it for the rest of this. So for the entire Cartan, well, the subset of the Cartan subalgebra that's annihilated by mu. And here is where you use this, this F1 is equal to 0. Okay, so in general, I'm going to have a general element here being the 0 part plus higher tails. But then when I look at the action here, it lives in G plus. It also lives in F. So that's in F1, but F1 is 0. Okay, so that's telling us that the kernel of mu, which is a subset of the Cartan, subspace of the Cartan subalgebra, is entirely in F0. And now it's the same sort of story as before. Okay, take a complementary subspace, deformation map of positive degree. Admissible weights are multiples of mu, opposite sign sort of things. So for the case where you're deforming these directions, well, all your weights are non-negative. That kills this delta. The more technical part is these other directions in A0. That I won't discuss here. It's more technical, but it's not too difficult either. Then you have to determine curvature. But same sort of argument, you get the canonical curved model. Okay, I'm running out of time, so let me just skip this part. Happy to share slides. Just a quick summary. So we used a Cartan theoretic approach to establish a local uniqueness result for submaximally symmetric models. Coordinate models are associated to some of these canonical curve models are known. So in the settings of projective structures, this was due to Egorov, but you're not going to find a uniqueness statement there. Okay, so he got the submaximal symmetry dimension, he exhibited his model, but stopped there. Split conformal structures. So a model due to Casey-Donaski-Todd in signature 2.2, dimension 4. If you tack on a flat factor beyond that, that also gives you submaximally symmetric models. G contact structures, these coordinate models were stated in a paper I wrote in 2018, like the E8 contact structure. How do you write that down? C3 Monge, studied by, Anderson and Norowski. Legendrian contact structures or para-CR structures. This work with Dubrov and Medvedev. Advantages of the Cartan theoretic approach. You have an efficient and uniform classification strategy. And we really take advantage of this basic representation theory of G. Things can be done by hand here. Okay, so I think I will stop there. Sorry for going over time. Thanks.
So we have time for only a quick question. If I have longer question, I would suggest to postpone that to the discussion afterwards. So
Big question. Are there examples that the submaximal symmetry algebra is semi-simple?
Submaximal symmetry algebra is semi-simple. Yeah, so in second order ODE case. Yeah.
You know these?
Yeah, I gave an example that one that was y double prime is equal to x y prime minus y all cubed. So that has SL2 symmetry.
And the maximal is?
SL2.
The maximal is SL2.
Oh, no. Maximal is SL3. Sorry, I misheard you. Submaximal, there is one with SL2 symmetry.
It is the only example, you know, yeah?
No, in CR case.
Yeah, I mean, three-dimensional CR is basically very similar.
Then you have both, because you have SO12 and SO3.
In what? Maximal.
Submaximal.
Yeah, maximal is SO3. No.
Maximal SU12.
SU12, yeah.
And the submaximal, there are plenty of submaximals.
Yeah.
And there are two semi-simple actually. There is one parameter family of CR, three-dimensional CR structure with the
Yeah, right. There is a one parameter family
three and
with
one
SL2s.
parameter
Yeah.
family with symmetric
Yep.
But he says that submaximal is unique.
No, but the assumption, remember, at rank 3, rank at least 3. Misha, the lowest cases are they're exceptional.
This is A2.
okay, anyway, I would really suggest to continue in the discussion session.
Yep.
So let's think again.